Hi there, grade 10s. Today we're going to discuss a brand new topic. It's called calculating the empirical formula of a substance. Now, for you to understand what the empirical formula is, I'm going to give you the definition and then look at some examples, and then we'll do some calculations. So the empirical formula gives the simplest ratio in which the elements combine to form a compound. Sometimes the empirical formula is the same as the true formula of the compound, sometimes it's not. Here we have some examples. Let's look at the examples. Water is a common compound with the formula H2O. This is the empirical formula. But the true formula or the molecular formula is also H2O. So the empirical formula gives us the ratio between the atoms as 2 hydrogens to 1 oxygen, but the true formula actually has 2 hydrogens and 1 oxygen in it. Let's use another example, hydrogen peroxide. Now, hydrogen peroxide's true formula or the molecular formula is H2O2. So the ratio in which the atoms combine is 2 hydrogens to 2 oxygens. But this is not the simplest ratio. The simplest ratio is 1 to 1. So the empirical formula for hydrogen peroxide is HO. This compound doesn't really exist. It just gives you the simplest ratio in which the elements combine. Usually, for ionic substances, the formula is the empirical formula. Like sodium chloride, the empirical formula is NaCl because 1 sodium joins to 1 chlorine. But this is not a molecule. It's a formula unit. It's the smallest part of the compound that makes up a salt. So all salts have, depending on the size of the crystal, it will have N ions of sodium and N ions of chlorine, whether you have a big block of salt or just a speck of salt. The empirical formula gives the ratio in which the sodium ion and the chloride ion has joined. It doesn't give the actual number of atoms or ions for that matter in the compound. Another molecular formula, for example, ethane. Ethane. Let's start with ethane. Ethane's actual formula is C2H6, but the empirical formula gives the simplest ratio between 2 and 6, which is 1 and 3. Now, this compound with this formula CH3 doesn't exist, but the simplest ratio in which the atoms combine is 1 to 3. Now, up to now, we've used formulas and calculated percentage composition from the formula. From this lesson on, we're going to use the percentage composition to get to the formula of the compound. So the first calculation, a compound contains 52.2% carbon, 13% hydrogen, and 34.8% oxygen. Determine its empirical formula. So this is a step-by-step method in how we will tackle this problem. You write down the symbol for the element. So the first element is carbon. The second element is hydrogen, and the third element is oxygen. Then we change the percentages. Now, the percentages would add up to 100%. We change the percentages to mass. And we would say in 100 grams, because they add up to 100%, we change the percentage to mass. In 100 grams, 52.2 grams will be carbon, and we write that mass below the symbol for carbon. 13 grams would be hydrogen, so we write 13 below hydrogen, and 34.8 grams would be oxygen. Now, in stoichiometry, everything is about the mole. To calculate the mole, we need to take the mass of the element and we need to divide it by the element's molar mass. So the carbon, we're going to divide the 52 by 12, and you get the mole ratio from there. So 52 divided by 12 gives us 4.33. 4.33 mole. Hydrogen, you divide by 1 and you'll get 13. Oxygen, you have to divide by 16 and you'll get just over 2. 34.8 divided by 16 is 2.175. 2.175. Now, we don't write the formulas with decimal fractions. So we need to find a method to change these decimal numbers to integers. So we change them to integers by dividing by the smallest. The smallest number is the 2.175. So I divide the 2.175 by 2.175 and I get 1. I divide the 13 by 2.175 and we get 5.977. The 5.977 is so close to 6 that I can change it to 6. Divide the 4.33 by 2.175. 4.3 divided by 2.175 gives us 1.9908, which is extremely close to 2. If the decimal numbers after dividing by the smallest number is close to the next number or close to the previous integer, then we round up or round down. So the ratio in which carbon has joined to hydrogen has joined to oxygen is 2 to 6 to 1. So the empirical formula is C2H6O. Right? We're going to go to the next example, and you'll see there is a pattern that we follow. A sample is analyzed and it is found that it contains 28% of iron, 24% sulfur, and 48% oxygen. Determine the empirical formula of the substance. So we write down the symbol for iron, the symbol for sulfur, and the symbol for oxygen. And because these percentages adds up to 100, I can say in 100 grams, there'll be 28 grams of iron, 24 grams of sulfur, and 48 grams of oxygen. In stoichiometry or analytical chemistry, everything revolves around the mole. So we are going to change the mass into moles so that we get the mole ratio by taking the mass of the element and dividing it by the element's molar mass. So the 28 must be divided by, for iron, is 56. For sulfur, it is 32. And for oxygen, it is 16. Now, I want to make a note here. We use the element and not the molecule O2's mass here, because that would throw out the ratio in which these elements, the atoms, have combined. So we don't look at the molecules, we look at single atoms when we calculate the empirical formula. Now, 28 divided by 56, I think, is 0.5 mole. And 24 divided by 32 is 0.75 mole. And 48 divided by 16 is 3 mole. We're nearly there. I can't round up or down with 0.5 and 0.75. So the next step to try and get them to integers is to divide by the smallest number, mole. So here we divide by 0.5, there we divide by 0.5, and here we divide by 0.5. And what do we get? We get 1.75 divided by 0.5 is 1.5. 1.5 is 1.5. And 3 divided by 0.5 is 6. We have a problem here in that this is 1.5. 1.5 is 3/2. I want you to do some mathematics. How can I cancel out the 2 that is dividing into the 3? This is how we do it. We multiply by 2 right through, and then the half will disappear. So 1 times 2 is 2. 1.5 times 2 is 3. And 6 times 2 is 12. So the empirical formula for this compound is Fe2S3O12. Right. So we've got the empirical formula right there. I'm moving on to the next one for the sake of time. A compound consists of 36.5% sodium by mass and 25.4% sulfur and 38.1% oxygen. They say by mass. Determine the empirical formula. So they have analyzed the compound with their mass spectrometer, and they discovered that if I have 100 grams of this compound, in 100 grams of it, there'll be 36.5 grams of sodium. There'll be 25.4 grams of sulfur, and there'll be 38.1 grams of oxygen. Next step is to change it into the mole. To change it into the mole, we take the mass of the element that we got from the percentages and we divide it by the molar mass. So sodium's mass must be divided by 23, sulfur's mass must be divided by 32, and oxygen's mass must be divided by 16. So we get the mole ratio. for this compound's elements. 36.5 divided by 23 gives us 1.587 mole. The 25.4 divided by 32 gives us 0.794 mole. And the 38.1 divided by 16 gives us 2.381 mole. To try and change the decimal numbers to integers, we divide by the smallest, which is 0.794, which will turn sulfur into 1. Divide the 2.381 by 0.794. 2.381 divided by 0.794, and you get 2.9987. Now this is very close to 3, so I'm allowed to round this to 3. So 3 moles to 1 mole, and the last one, 1.587 divided by 0.794 would give me, I think it should be 2. 1.9987, which is rounded up to 2. So the empirical formula is Na2SO3. And this one you should be able to recognize as sodium sulfite. Righto, let's go to the next one. This one's got a different kink to it. Here they say that you've got 207 grams of lead combining with oxygen to form 239 grams of lead oxide. Determine the formula for the lead oxide. Now it would be ionic. Let's go. The lead's mass is given as 207. So this one, they don't give us percentage composition. They give us the actual mass in the sample. And this 207 grams of lead reacted with oxygen. The lead oxide has a mass of 239. So to get the mass of the oxygen, we need to subtract the mass of the lead from the sample. So the mass of the oxygen, it looks like 32 grams. The mass we need to change into mole by dividing the mass of this element by the molar mass of the element. Lead's molar mass is 207, so this one I divide by 207, so I get 1. And this one's mass I divide by 16. Oxygen's mass divided by 16, you get 2. So the ratio, the mole ratio, sometimes works out nicely into integer values. So this is PbO2, which has the name lead 4 oxide, because the valency of the lead there is 4 if oxygen is 2 and there are 2 oxygens joined. If I can just snip in there, the valency of the oxygen is 2. There are 2 oxygens, so it's multiplied by 2. That gives us 4. So the valency for the lead must be 4. Right, let's move to the next example. Oh, the next example would be the next video. So I'm going to stop this video here.